Hello, everyone. How's everyone doing? Hope you all had a nice Thanksgiving break. Um, we're going to get started today with our warm up of today. We're starting the last sort of conceptual ideas behind for this semester. But for now, I just want you to answer this question here. Um, we have a Lambo that's racing a farm truck in this video. So there's actually a lot of these videos on YouTube. They're actually really, really, really funny. They're really cool too. But the Lambo, I think, I don't know what kind of Lambo it is, but it's a Lambo. It's racing a farm truck in the video. And in the chat, I want you to answer which car do you think is faster, and then I want you to answer how would you measure the speed of either car. So let's get some answers in the chat here, and let's see if we can get some ideas. So which car do you think is faster, and then which how would you measure the speed of the car? Okay, let's see. What? There's so many people who believe the farm truck is gonna win. That is wild. That is wild. if you've seen the video, boo! You're not supposed to see the video. You're supposed to. You're not supposed to see the video. That's stupid. You're supposed to not see the video. Um, no, the Lambo's gonna win. It's the Lambo's gonna win. It's a freaking Lambo, guys. It's a Lambo. Why would a farm truck beat a Lambo? Come on. Come on. You are all just you. I don't know what you guys are on, but there's no way a farm truck beats a Lambo. Um, don't underestimate the farm truck. No, do you win, Shawnee? I don't know. I don't know. I don't know. We'll see. Um, the other one is speed, the other one is stamina. Could be, could be, could be. Okay, well, wait a minute, just to see if we get some more ideas here. We got a lot of people thank you, thank you. I cut my hair myself nowadays because of COVID, so I did my best. The good part about a buzz cut is it's hard to mess up, so I appreciate that. I want to see the other one is stamina. Wow, yeah, wow, yeah, wow. That's farm truck built different. Um, it is built different. Okay, so we're gonna watch this video here because farm trucks are interesting to watch. Okay, so where is it? I have so many tabs open that it's like low key hard to manage. Okay, all right, here we go. I'll actually just put a link in the chat so you can watch it because it's kind of laggy right now. I realize when I'm but I still will share it though because it is interesting. So where were we? I know. I'm sorry. I'm trying to figure out the lag here. I don't know if it's a bandwidth thing. So one of the commentators was the funniest thing. The commentator was like, "You buy a Lambo for 200 grand, and then you could buy the farm for 20 bucks." So, Yeah, so the farm truck absolutely wrecked the limb. Okay, so the point of this was to like shock all of you, be like, "Whoa, Mister Who? What? The farm truck beat a Lambo? What? What am I supposed to spend my $200,000 on?" No, you spend 28 bucks on a farm truck and get a nice engine. Yeah. So my advice for you is when you all become rich and famous, spend 28 bucks on a farm truck and don't waste your money on a Lambo because the farm truck will destroy the Lambo every single time. Um, Also, yeah. So don't. Also, is if I okay, I just closed something. Is this better? Is this better? Is this less laggy? Okay. Uh, okay. Well, I'll keep trying to figure it. Okay. So, okay. Anyways, um, is it because it's heavier once in motion? It does keep moving. That is true, and we will talk about that concept later on, James. But right now we won't quite get to that yet. We'll instead just talk about a little bit about speed, um, about why one is faster than the other. So, hopefully you all had a little bit of fun. I had quite a bit of fun here. I didn't have as much fun as I would like because you all like ruined the video because apparently. Okay, so we're gonna talk a lot about speed and velocity today. So we're gonna talk a lot about how fast things move. And so what I want you to do is I want you to take notes using the provided note sheet again and submit it to Canvas whenever you're done. Um, and I will also link something to the slides as well. So if you want to follow along on your own computer, not on mine, that's good because I'm struggling. Oh, sorry, that's the wrong one. That's the wrong one. Those are the wrong slides. Those are from my AS class. These are the correct slides. That was from my AS class. I apologize. Um, yeah, so take notes using the provided note sheet and submit them to Canvas. I should be covering most of it, just that way you all get to fill along. I actually don't think we'll be able to finish all of it today, so you don't have to submit it today. I think we'll submit it on Friday, but we will get through most of it. And then there also are, I sort of realized as I was going to teaching fifth period yesterday that there were some important concepts that I didn't uh, put on the note sheet, but there are important. So I do want you to try to take notes on that. I didn't have a space for it in my note sheet, but I do want you to take. I'll let you know when that comes up. But there's a couple of important concepts here that I didn't put in the note sheet, so we will cover that as well. And before we get started, due dates. So any assignments you have, you should submit them. But by the end of the semester, there is a hard deadline this time. End of the semester. I'm not really trying to do a lot of grading over winter break. So submit everything by the end of the semester. That includes any revisions, any missing assignments. So please do that by the end of the semester. If you have any questions about missing assignments or how you're doing grade-wise or what you should do, just reach out to me and I will do my best to answer your question. Okay. So we'll get started with today. So let's talk about what is speed here. So what is speed? Well, first off, the truck absolutely destroyed the Lambo. And the truck destroyed the Lambo because it was faster, right? And it was faster because it drove the same amount of distance in a lot less time. So they both were starting from the first cones to the second cones. Um, but the truck destroyed the Lambo because it just drove the same amount of distance in much less time. So therefore, we can say that it was faster than the Lambo. Um, in other words, speed, right? Speed just measures how fast an object is moving. And so we can measure the speed of an object by looking at how much distance it can cover in a certain amount of time, right? So if an object is moving faster, it covers more distance in the same amount of time. And if an object is slower, it covers less distance in the same amount of time. And I think these conceptually, I think feel like we have a good understanding of speed. But mathematically, the way you calculate speed is you calculate speed by taking the amount of distance you cover and dividing it by the amount of time, right? So if you're covering more distance over less time, you're gonna have a higher speed. But this idea of how to calculate speed is very important. Remember that speed is distance over time, and that speed measures how fast an object is moving by looking at how much distance it can cover in a certain amount of time. Okay, so Move on. Okay, so let's talk a little bit about some examples of speed because you've definitely seen some examples before.
Can you go
Oh,
back?
second one. Okay, second one. Second one. So we can measure the speed of an object by looking at how much distance it can cover in a certain amount of time. That's the second bullet point. We can measure the speed of an object by looking at how much distance it can cover in a certain amount of time. All the information should be on the slides themselves. So if you're ever unsure of something, you can just look at the slides that I've linked and you should be able to find it there as well. Okay, so let's talk a little bit about some examples of speed. So some examples of speed. So you've definitely seen a speedometer before on your car. So why is it called a speedometer? Because it's a meter that measures the speed of your car, right? So if you're driving 60 miles an hour on your speedometer, it just means that in 1 hour you can drive 60 miles, right? So you have a speed that's equivalent to your distance, which is 60 miles divided by your time, which is 1 hour. In physics, we don't like to use miles an hour. We like to use meters per second. Very, very, very important. Use meters per second. So if you're running at 5 meters per second, that means you can cover 5 meters every 1 second. So in 2 seconds, you can cover 10 meters. In 3 seconds, you can cover 15 meters, et cetera, et cetera. But that I think is fairly straightforward. The harder idea is that recognizing that speed can only be positive, right? So if you've ever backed up in your car, if you look at your speedometer, there is no negative speed, right? It still shows your speed as being positive. And that's because speed can't be negative, right? It doesn't really make sense to say you're driving negative 20 miles an hour because that doesn't really make any sense, right? What matters is just how fast you're going. So speed only cares about how much distance you're covering. It does not care about your direction. So the negative tells you a direction, but speed does not care about direction. It only cares about just how much distance you're covering. So whether or not you're going right, left, up, down, speed is just speed. It's just how fast you're going. All right. So our next thing, a little bit of a conceptual problem. We are going to feature our my beloved friend Khalid here, who I'm definitely friends with. So Khalid, he's on a trip with his girlfriend, and he just wants to make sure that they're starting off right. He wants to make sure, which he just wants to talk and figure out where they're going before they get lost. So they travel 200 meters in 40 seconds before Khalid apologizes for going too far. So what is Khalid's average speed in this problem? I just want to figure out where we're going. Before they get lost, they travel 200 meters in 40 seconds before Khalid apologizes for going too far. Where they're going. So they travel 200 meters in 40 seconds before Khalid apologized for going too far. What is Khalid's average speed? So how can we figure out speed? Remember that speed is distance over time. So take a couple minutes and then whenever you're ready, put your answers in the Zoom chat. What is Khalid's average speed here? Let's get some ideas here. We got a few. Ooh, we got so much participation. I'm super happy. We've got so many people here. We've got Shona, Adriana, Alex, Sebastian, Melissa, Jasmine, Mariana. Ooh, we got so much participation. So I'm super excited. Love seeing it. So how do we figure this out? Nice job, Alejandro. Great job. Good work, Mariana. So how do we figure this out? Oh, Namalia coming in strong here. James, good job. Wow. Oh, so much participation. Super happy. So we travel 200 meters in 40 seconds. So which means that our distance, 200 meters, we're traveling in 40 seconds, which is our time. So you take your distance divided by time, 200 divided by 40, and that's just 5. So 5 meters per second. Just remember your units. Our units here are meters per second. That is very important because we want to make sure that we know what we're talking about here. So great job, everyone. Loving it. And so we're going to move on to our next sort of idea here. We're going to talk a little bit about something called velocity. So velocity is very similar to speed, but it's a little bit more complex. So we want to make sure that we really understand it. So velocity is the speed we're going in a certain direction, right? You need to have a direction when we're talking about velocity. So let's say a cat is moving at 600 meters per second. Well, what I'm saying when I'm saying a cat is moving at 600 meters per second, we are specifying the cat's speed. We're talking about a speed. However, if I'm saying that the cat is falling downwards off of the Empire State Building at 600 meters per second, we are actually specifying the cat's velocity. And that's because the cat has a certain speed, 600 meters per second, in a downwards direction. By telling us the direction, we are actually specifying the cat's velocity. Now, before you say, Mr. Who, you're so morbid, you're a horrible person, just remember that cats have 9 lives. So if they die, they have 8 more lives. Also, additionally, cats are also very good at falling. So like cats are actually like cats can fall from a ridiculous height and be totally fine. It's actually really weird. So the cat here, don't worry, the cat's gonna be fine. And even if they aren't fine, they have 9 lives. But the key idea here is not about how many lives the cat has, but it's actually about idea of velocity. Cats have cats, but there's a velocity. You have a speed, 600 meters per second, and you have a direction. In this case, it's downwards. It's falling off the Empire State Building, which is very cool. So when we look at velocity, we're actually looking at how fast your position is increasing or decreasing. Your position, not your distance, your position is increasing or decreasing. So another way of saying this is that your velocity is your displacement divided by time. Velocity is displacement divided by time. If we don't remember what displacement is the change in position. So if your position is changing, you have a displacement, which means you have a velocity. So velocity relates to displacement, and displacement is change in position. Very, very, very important. 100% remember that. And because velocity relates to how fast your position is increasing or how fast your position is decreasing, velocity can be positive or it can be negative. Unlike speed, you can have a positive velocity or a negative velocity. If you have a positive velocity, that means your position is increasing, becoming more positive. And if you have a negative velocity, it means your position is decreasing, it's becoming more negative. Usually, what happens is where we work in, right is positive, left is negative. So if you have a positive velocity, it generally means that you're moving to the right. If you have a negative velocity, it generally means you're moving to the left. We like to set it positive and negative direction. So your velocity is literally just what direction you're going in. And in that regards, I think it's actually a little bit easier than displacement. Just talk about what direction you're going, and it relates to what your change in position is. Just remember, the velocity is your displacement over time, and then your displacement is your change in position over time. All right, so we're gonna go to another problem here. It's a TBT, Throwback Tuesday. So back when Mr. Who was in high school, this was, I don't know, 100, 200 years ago. So I needed to go to someone to prom. So the problem was back in the day, back in the day, we didn't do in-person askings either. What I did is I went on Craigslist and I typed in nearest human. And I say looking for nearest human to go to prom with me. And I found that the nearest human was 1,000 meters east of me. So I run 1,000 meters east in 10 seconds. I reach the human. Once I reach the human, I figure out that I got catfished, boo, and that the human wasn't real. I then run 2,000 meters west in 10 seconds to go yell at kids to get off my lawn. What is my average velocity? So this problem is actually kind of tricky because I realized that there's a few different ideas here. I'm going to give you a couple minutes just to try it out. But I will go over, there are a lot of different ideas behind this because I sort of realized that there's a lot more nuances for this. So I'm gonna give you a few minutes just to try it out. I'm going to set up the problem on the board. That's actually a good idea, James. Here's what I want you guys to do. I will actually go over everything in a second. I want you to first just figure out the two speeds themselves. Figure out the two speeds themselves, the two velocities themselves, and then we'll look at the average velocity. This problem is actually a little bit more complicated than I intended, and I will go over it on the board. But I just wanted to give it a try it out. See if you can figure out any one of the two individual velocities, and then we'll take a look at the overall. Okay, so here's what happens. So here's what I'm going to do here. Then sort of realize this problem is a little bit more complex than I intended. So we're actually a few different velocities here. You have one velocity for when you're going right, and you actually have a different velocity from when you're going left. Because we cover both in 10 seconds. This one in 10 seconds, and this one in 10 seconds. So it logically just makes sense that we're moving faster than we can. So we actually have two different velocities. And then we actually have an average velocity for the whole trip in general. This is actually more complex than intended. And I'm just going to show you what I mean by each thing. So first, what I'm going to do is I'm going to take a look at my velocity going right. So how do we figure out our velocity? Well, our velocity relates to our displacement. And our displacement, if you remember, is our change in position. So the best way to start this off is let's first identify with our initial position. Our initial position, well, we're starting at 0. Start at 0. So ending position. Our ending position, while we go 1,000 to the right, we call it 1,000 east. Our ending position is plus 1,000 meters. So what is our displacement? Our displacement, well, our position shifted by 1,000. So our displacement is also plus 1,000. Okay. So now let's figure out our velocity. So if you're unsure about how I got displacement, our displacement is our change in position. So in this particular example, I just looked at my initial position, which is 0, my ending position, which is 1,000, and the difference between the two is 1,000. Another way of thinking of it is I just moved 1,000 to the right, in which case you don't even need the initial and ending position. If you just recognize that if you just moved 1,000 to the right, your displacement is going to be 1,000. So our position is 1,000, the displacement is 1,000 here. Let's figure out our velocity. Well, our velocity is our displacement over our time. Our displacement here was 1,000. Our time was 10 seconds. So our velocity is actually 100 meters per second. Now I'm going to put a positive here to let you know that we're going to the right. This is very important because velocity needs to have a direction. If you just say, 10 or 100, I don't know what direction you're going. So it's very important. The positive is a direction. Very important. Okay, now let's take a look at the left one. The left one's a little bit trickier. I'm going to show you how I do this. So what's our initial position? Well, for the left one, we're not starting from 0 anymore. We're actually starting from here. So our initial position is actually positive 1,000, right? Well, what's our final position? Well, we go 2,000 to the left. So if we started at positive 1,000, we go 2,000 to the left. Our final position is actually negative 1,000 meters, which means our displacement is negative 2,000 meters. So how did I get my displacement? Well, to go from my initial to my final, I have to go 2,000 to the left. So that's just negative 2,000. And another way of thinking about this is I just went 2,000 meters to the left, west. So that's just negative 2,000 meters for my displacement. My velocity is my displacement over time. Write out the formula again. So that means our velocity is negative 2,000. So displacement is negative 2,000, which is 2,000 divided by 10 seconds again. So our velocity is actually negative 200 meters per second. Again, this negative is very important because this negative tells me a direction. So that I think makes sense, right? For the most part, we just look at velocity of each individual section. What happens when we look at our velocity as a whole, as an average? Well, it's sort of the same idea, except we don't necessarily care about the in-between. We're looking at the average velocity. We care about where we start at the very beginning. And we care about where we end at the very end. So where are we at the very beginning? At the very beginning, we are at 0, right? We start from the very beginning, 0. Where at the very end? We are not here. We are actually all the way back here. So at the very end, we are actually at negative 1,000 meters. So I mean, our displacement, our total displacement, we call this total dis. Our total displacement is actually negative 1,000. So to figure our average velocity is equal to our total displacement over our total time. This is equal to negative 1,000 over 20. So our average velocity is negative 50 meters per second. Again, I have the negative to show a direction here. So this is our average velocity. This is our velocity for when we're going left. This is our velocity for when we're going right. What I'm also going to show you is how we can take a look at the average speed and distance. So this part right here, this isn't really on your notes, on the note sheet I gave out, unfortunately, but this is something you should 100% write down, 100% remember. This, I believe, this should be on your notes, this idea here. But I'm also going to show you how we can figure out our average speed, which is, again, different than our average velocity. Because whereas an average velocity, we only care about where we start and where we end. For the average speed, we actually care about how far we went in total. So where our displacement was negative 1,000, because we started here and we ended here, our total distance is we went 1,000 to the right and then 2,000 to the left. And this is equal to 3,000. Okay, so our average speed is not too bad. This is just our total distance divided by total time. So our average speed is 150 meters per second. I don't really need a positive or negative here because speed does not have a direction. We don't care. Same with our distance. We don't care about direction. We only care about the number. So that's how you figure out average speed. For average speed, we need to look at how far you went in total. For average velocity, you care about where you start, where you end, the very end. And then for your velocities with individual segments, you only need to look at the individual portions. But there's a good amount of a good amount of information here, But I think hopefully it's not too bad. So does anyone have any questions about this part? Anyone have any questions about how I did some of this? Hopefully I didn't rush through it. I'm not sure everyone sort of has an idea. So I'm just going to leave this up on here just for a little bit, just so we all have a chance to keep writing some stuff down. And I'm going to start moving on to the next part. So let's take a look at an example of velocity here. So let's look at some examples of velocity. So that was an example of velocity here, and this is just another example here. In this example here, this is Khalid. This is the same example as this one. I start at 0. My position was 0. At 10 seconds, my position is 1,000. At 20 seconds, my position is negative 1,000. So my average velocity was just my total displacement, which is negative 1,000, divided by my total time, which is 20. So that's how I got my average velocity, which is negative 50. And then for my total average speed, my total distance was 3,000, which is kind of tricky. My total time was 20 seconds, and my average speed is 115 meters per second. I just want you to notice how velocity can be positive or negative. And you also need to include a direction for a velocity. Because otherwise, I just don't know which direction it's going. It's like a velocity is like it's very important to know your direction. Okay. Okay, so For this next one here, um, so for first off, I just want you to, in your own words, write down the difference between speed and velocity. You don't have to share this with the class. I just want you to try to write a definition that makes sense to you, so that you can remember it, so that when you look back and read it, it makes sense to you. There should be a space for that in your note sheet. Write down a definition. Write down what you think is the difference between speed and velocity in a way that makes sense to you. Because I feel like sometimes if I give you a definition, it may make kind of sense, but when you look back on it, you're not really sure. It makes a lot, it helps a lot to write your own, in your own words, write down the difference between the two. And then whenever you're done, you can take a look at the second question here. We have Owen Wilson. So Owen Wilson and Keanu Reeves are in this Academy Award winning film called Bill and Ted's Excellent Adventure. It won so many Academy Awards. Sorry, go ahead.
Absolute classic.
Absolute classic, yes, absolutely. You get extra credit if you watch it. They released, the third one is supposed to come out soon. Keanu Reeves does not age at all.
But they did the second one. That was pretty recent though.
The second one was like a back to like straight to DVD thing, I think. I think I tried watching the second one.
Yeah.
I think I tried watching it, but I don't think I ever finished. But the first one's an OG classic, very OG classic. That's how you learn history, by the way. I don't know who plays, I don't know if Owen Wilson plays Bill or if Keanu Reeves plays Bill, but either way, one of them is Bill, the other one's Ted. And so if they both of them, if they have a car, we got Owen Wilson's car moving northward, and it reads 400 meters per second. Keanu Reeves' car is traveling southwards at 400 meters per second. So do both cars have the same speed? And do both cars have the same velocity? So this one you should answer in the chat. The first one you just answer by yourself. The second one, let's get some ideas. Do both of these cars have the same speed? Or do both of them have the same velocity? Or both? We don't know. We don't know. Are they starting equal distance apart? What I'm going to say is for this problem, I don't think it actually matters how far they start apart. Because both cars have a speedometer. Both cars have a speedometer. Speedometers are both 400 meters per second. So using that, both cars have the same speed. They have the same velocity. Whenever you're ready, let's get some ideas in the chat here. Do they have the same velocity? Do they have the same? We'll take another minute to get some more ideas here. I should start doing polls. Polls might be good, but I like reading what people have to say. Ooh, we got a lot of different ideas here. I like what I'm seeing. I like what we're seeing. I can clearly tell. There's a lot of good thinking here. There are a lot of big brain moments. Take another minute for you to ponder this. Owen Wilson and Keanu Reeves, their speedometers are both 400 meters per second. Oh, nice. All right. So here's what I'm going to say. I'm going to sum up what everyone has said here. I actually really like what Alex's definition is, but I also really like what James is saying. And then Miles is showing me I really like what you're saying as well. So both cars have the same speedometer. They're both saying 400 meters per second. So they're going at the same speed. So both cars have the same speed. That's what James said. I totally agree, right? Both cars, they're both going at 400 meters per second. So they both have the same speed. However, one car is going like this, And then the other car is going like this, right? One's going north, one's going south. So they have two different directions here. So they actually have different velocity. Same speed, different velocity, which is what Shoni was saying. And now I really like what Alec was saying here too. They have the same speed, but one velocity is negative and one is positive because they're going in opposite directions, which is 100% true. Very good analysis there, Alec. Thank you for sharing. So I really like what I'm seeing here. Yeah, both cars at the same speed, but different velocity. And this is something that can be kind of tricky. So we want to make sure we get it now. We got another problem here featuring me, yours truly, Mr. Who. So here's what happens. So I decided I'm going to go 7 inches taller because that's a choice. You can choose to go 7 inches taller. And then I gained 60 pounds of muscle. So I'm actually shredded, absolutely yoked right now. So with my newfound athletic ability, I say, forget teaching an MA. I don't want to teach an MA anymore. I'm going to go play in the NBA. And then I get signed by the Boston Celtics. I'm actually not a Celtics fan because I don't like the Celtics, but I'm using it for the story here. Because in the 2008 NBA Finals, Paul Pierce has a quote unquote knee injury. And so because he has a knee injury, yours truly, I get to play 30 seconds in game one. And then Paul Pierce miraculously comes back to ice the game to win the game for the Celtics against the Lakers. The legend has it that Paul Pierce actually faked his injury so he could go to the bathroom. That's a legendary.
Which one?
Which one?
The one in the finals against the Mavs.
No, this was against the Lakers, 2008.
No, because there was one of them he actually admitted.
I think that was okay. So I think that was actually against the Lakers. I think he admitted that he had to go to the bathroom. I'm not sure if he was just trolling or if that was actually true. But he did admit that he had it, that he faked an injury to go to the bathroom. More specifically, he may or may not have had an accident in his pants, in his shorts. That could be true. We'll see. But again, the point of this is I played in the NBA for 30 seconds in game one of the NBA Finals. Okay, Mr. Who Wise is relevant. So here's what happened. In my 30 seconds of playing time, I ran 4 meters east, 2 meters south, 2 meters west, and 2 meters north. So I want to figure out what is the total distance I traveled, what is my total displacement, what is my average speed, and then what is my average velocity. So for reference, I start in the top left corner. I go 4 meters east, I go 2 meters south, I go 4 meters west, and I go 2 meters up, 2 meters north. So what is the total distance I traveled, which I think is doable? What is my total displacement? A little trickier. My average speed, I think not too bad. And then my average velocity, which is kind of tricky. So let's start with bite-sized chunks. What is the total distance I traveled? Can I get some answers in the chat? How far did I go in total? And 4 meters east, 2 meters south, 4 meters west, 2 meters north. What is the total distance I travel? We got one answer from Shone. Can we get a few more answers in here? I just want to get a gauge to see where people are at. Helps me a lot when I sort of have an idea. Ooh, Sebastian, we got James. Oh, Shone, labeling your units. Great work, Shone. James, great work. Total distance. I like the vocabulary. Can we get a couple more answers? Okay, James, jumping ahead. Nice work. But we'll get to displacement in a second. Let's give it another 30 seconds for people to figure out the distance, and then I'll go over how we do the distance in 1 second. Ooh, we got Miles, we got Alex. Great work, guys. Coming in strong here. So we got Mariana. Great work, great work. Loving what I see so far. Let's give another 30 seconds to fucking wipe the board here and give us a visual of how we do the totals. If you figure out a total distance, you can get a jump start on the total displacement. You can get a jump start on it while I wipe the board here and get ready to tackle this total distance problem here. All right, so we got Melissa. Good work, Melissa. Okay, so let's take a look at my total distance here. So I'm gonna say I started here. I go 4 meters here. I go 2 meters here. Go 4 meters here. I go 2 meters here. So what's my total distance? Well, my total distance is 4 meters plus 2 meters plus 4 meters is 2 meters, and that is equal to 12 meters total. Good work, all of you, figure out our total distance. So let's take a minute to figure out our total displacement. We've already got a few people who've gotten a jump start on displacement, which I like, but we will take it, we will go in a little second. We'll talk about displacement in a second. Let's see if we can figure out what our total displacement is. If you're unsure what displacement means, I'm gonna give you a little hint. Displacement is the total change in position, right? Where do we start in the beginning? Where do we start at the end? And use that to figure out our total displacement. We had a few ideas over here. We got Mariana, we got Shoni, we got Miles. I think James also had an answer earlier. James jumped ahead. Good work, James. Can we get a couple more answers, a couple more participants? Producers did a great job. I want to keep it the momentum. And then we'll talk a little bit about displacement in a second. Displacement is one of the trickier things, one of the trickier concepts to understand. This idea of the change in position. I think distance is a little bit more straightforward. I think displacement is a little bit harder. Now I'm just gonna quickly visually show you where displacement is. Okay, so we started here. We went around here, we went around here, we went around here, we went here. Where did we end? We actually ended in the exact same location. So if we start and end in the exact same location, our total displacement is, guess what? 0. What? No way. Yeah, way. Our total displacement is 0. If you start and end in the exact same location, your position never technically changed, right? You may have gone somewhere, but you ended in the exact same location. Good work. All right, so let's take a minute to figure out our average speed. We've already had a few people who are jumping ahead, so good work. But I do want to give people a chance to figure out our average speed. So let's see, remember, so let's try to figure out our average speed here. We want to keep our units in meters per second. So what is our average speed? Take a minute. Oh, we got a few ideas so far. We already got Miles, we already got Shoni, right, Mariana. I feel like we're all just like ready to go here. We got James here, who's also jumping ahead. Great work, James. So James did a good job here. He had his units at 24 meters per minute, which is absolutely correct. And I like that. It's a good way of thinking about it. Whereas Shoni, Miles, and Mariana, they use meters per second. So that's also a great way of thinking about it. Ideally, let's try to keep things in meters per second, just as a way of consistency. But all of you are correct. All of you are correct. And I'll show you how they did it. So our average speed is our total distance over our total time. Our total distance is 12 meters. Our total time is 30 seconds. So 12 divided by 30 is just 0.4 meters per second. That time, average speed. And then we have and then let's figure out my average velocity, my velocity. We've got Miles, we got Shoni, we already have some ideas. We got James with an idea as well. Got a couple of ideas for velocity. Again, it's okay if you aren't sure. I like guesses. Guesses are really good. So we got a few ideas for velocity and velocity. Take a little minute. All right, so for average velocity, we're going to take the integral of 5 dx, and then we're going to take the limit of 0 to 100, and then we're going to take this, and this is what, 5x, and 100 to 0. I'm just kidding. We don't actually have to do any of this. I'm just messing with you. Our average velocity is just 0. I don't actually do any math. I was just flexing my calculus. I'm sorry, I apologize. I had to do that. I got bored. So our average velocity is just 0. Because if our displacement is 0, our average velocity also has to be 0. We never really go anywhere. So our average velocity is just 0. Yeah, so yes, average velocity is just 0. We never really went anywhere. So good work, all of you. I really like what we're just seeing. I really like what we're seeing here. So let's see if we can keep this up. So again, my distance is 12 meters. My total displacement is 0. My average speed is just 12 divided by 30. 6.4. And then what is my average velocity? Is 0 meters per second. So good work, all of you. So let's talk a little bit about this idea of what does it mean to have a constant speed. So what is constant speed? I think I might have already introduced this a little bit, but constant speed just means your speed is not changing. You're constantly moving at the exact same rate. You're not speeding up, you're not slowing down. You just have a constant speed the whole time. It's like if you're driving, you put your car in cruise control, right? That's constant speed. That literally is what constant speed is. Constant velocity is different. Constant velocity, because velocity is speed in a direction, you need to have a constant speed and you need to have a constant direction. What constant direction means is you have to have, you're driving in a straight line. So in order to have a constant velocity, it means you're in motion in a straight line at a constant speed. So not only are you in cruise control, you're never touching your steering wheel. If you touch your steering wheel, you're changing your direction, which means you're no longer in constant velocity. This can be kind of this. I think that's the best metaphor to think about. Constant velocity means if you touch your steering wheel, you're not at constant velocity. The only way to have a constant velocity is what we call truck driving. When you close your eyes and you hit the gas pedal and you hope that you're driving straight. Don't do that, by the way, but it's a good metaphor. You're just driving in a straight line with your eyes closed and you're going to steer. Don't do that, by the way. So that's what constant speed and velocity means. It just means you're never speeding up or slowing down. The reason why this is important is just because in this unit, we're working with constant speed and velocity. So within any particular segment or section, the velocity or speed is going to be constant. But well, in the previous problem here, when we were talking about our friend, when we talk about me and my prom date and my yelling the kids to get off my lawn, you notice that my velocity did change. But within each particular section, it was the same. So that's the key idea here. So when you're at a constant velocity, within the section, it's the same. Okay, so let's say my Prius is doing donuts. I'm driving in a parking lot. I got my driver's license. I decided to do donuts. The best way to celebrate. So I'm driving donuts, driving a circle at a constant speed. Is my car also driving at a constant velocity? I'm gonna get some answers in the chat here. Get some reacts. Am I driving at a constant velocity? My car is driving at a constant speed. I'm driving in a circle. Any ideas? Am I driving at a constant speed? Am I driving at a constant velocity? If I'm driving in a circle. If you're not sure, but remember that constant velocity has a lot to do with constant direction. What is constant direction? Am I driving at a constant velocity? Joni says no. Does someone say yes? Anyone say yes? Well, here's what I'm going to say. In order to do donuts, in order to drive around in a circle, you actually, believe it or not, you actually have to touch your steering wheel. If you touch your steering wheel, you're turning your car, which means that your car is no longer driving at a constant velocity. So in this problem, even though I'm technically driving clockwise or counterclockwise, my car is not going at a constant velocity because I have to touch my steering wheel. James, you might want to mute yourself if you're playing Christmas music. Okay, so anyways, okay, so we're talking about. So I don't think we'll quite finish this today, but I will just do a little bit of a rundown here of graphing. So with distance and displacement, velocity and speed, we can all graph these as graphs, as XY graphs with respect to time. And we did a little bit of sort of visualization with number lines. We can actually do the same thing with the graphs with respect to time. So let's say I decided to graph a distance versus time graph. What does it mean to graph a distance versus time graph? What it means is I'm graphing how far I traveled in total at any particular point in time. The slope of such a graph, of a distance versus time graph, is the speed, right? And the slope of a graph means the change. Rise over run just means for every x, you're changing by so much y. So the slope of a distance time graph just basically tells you how much distance you go in a certain amount of time, and that's your speed. So the slope of a distance versus time graph is your speed. However, we can also graph a displacement versus time graph. And a displacement versus time graph tells us how far you are from your beginning position at any point in time. So a distance versus time graph just tells you how far you went in total. So your distance versus time graph is always going to keep increasing or to stay the same, because you can't ever decrease the amount of distance you've gone. Our displacement graph versus time graph, though, is how far we are relative to our beginning position. And I'll show you a visual for this. I can't visualize it now. I'll show you a visual for this. It just measures how far we are from our beginning position at any particular point in time. And the slope of such a displacement versus time graph is our velocity. So the slope of a distance versus time graph is the speed. The slope of a displacement versus time graph is the velocity. Now, if I ever ask you to find the speed of a displacement versus time graph, the speed of the graph is actually the absolute value of the velocity. What is an absolute value? An absolute value just means it's always positive. So if your velocity is positive, right, then your speed is the same thing as your velocity. If your velocity is negative, then your speed is just positive of that, right? So if your velocity is -5, the speed of that would be +5. And this is when you're talking about slopes for displacement versus time. And so, and the steeper slope you have, the faster your speed is. It just means your position, your distance is changing faster. So I'm going to move on to the next one just because I know we're all visual learners, and this isn't very visual. So this right here, I have a graph here, and I'll read the story here. So in the story, so back in my day, I don't know if I ever told you, my life was very hard growing up. And this is because every day for school, I would walk barefoot through the snow. So by the way, I'm from the Bay Area, right? So it snows a lot in the Bay Area, as you know. So every day I walk to school, I walk barefoot through the snow, uphill both ways on a straight home road from my home to school. Uphill both ways. My life was very, very, very difficult, much more difficult than all of yours because I walked barefoot through the snow, uphill both ways on a straight road from my home to school. So this graph shows my journey on one particular day. So what I have here is I have a displacement versus time graph. I have my displacement on the y-axis and I have a time on the x-axis. The displacement tells me how far I am from my home at any particular point in time, and then the time just tells me what time it is. So I have 4 questions right here for you. Let's first start with question 1. What is my displacement at the very end? At the very end, what is my displacement? So let's get some answers in the chat here. What is my displacement at the very end? And if you're unsure what this means, it means that how far am I relative to my initial position at the very end? This can be kind of tricky. Our displacement is just where our position is relative to where we started off. It's not how far we went in total. It's how far, where we are relative to our initial position. I'll give you another minute or so. We got a few ideas. So we got a mix, a spread of ideas here, which I like. I like having a lot of different ideas here because it means that we're thinking this. We're thinking about this, and I like that. So we got Viviana was a good idea. We got James with a good idea. We got Shona, Kat, Adriana, Miles. We got a bunch of good ideas here. We'll take another minute or so to get some more ideas. We got Mariana joining the club here. We got a lot of ideas so far, and I like that. I like seeing a lot of ideas here. So what is our displacement? Again, our displacement is our position relative to where we started off from. So I'm going to start narrating this story before I answer this question. So in this story, at 10 seconds into my journey, 10 seconds into my journey, I'm 20 meters away from home. 20 seconds into my journey, I'm 40 meters away. I keep going. At 50 seconds, I'm 100 meters away from home, right? So displacement just literally just tells us how far I'm away from home. Now this next section, my displacement is actually decreasing, which means that I'm moving backwards here now. So at 60 seconds, so at 70 seconds, I'm at 40 meters. So what that means is that within that time, I actually walked backwards 60 meters. So at 70 seconds, I'm 40 meters away from home. Another way of seeing that is my displacement at 70 seconds is 40 meters. And then from 70 seconds, at 80 seconds, I'm 80 meters away. I walk forwards again. In 90 seconds, I'm at 120 meters away. And at 100 seconds, I'm at 160 meters away. And then at 110, 120, I don't move anymore. I'm at 160 the whole time. So, what is my displacement at the very end? Well, my displacement at the very end is 160 meters. And that's because my position, how far I'm away from home, is 160 meters, right? When I'm at the very end, I'm 160 meters away from home. My total distance will be a little bit different, but my position, my total position will be 100. Okay, so now let's talk about when are we walking towards home. We got Miles here jumping ahead. Great work, Miles. But I want to give everyone else a chance to do this as well. So when am I walking towards my home here? I think I might have already have given you a hint. But when am I going towards my home? What I'm looking for here, I want you to tell me between what times am I walking towards my home? Between what time am I walking towards home? So we'll take a minute here to figure out when I'm walking towards my home. We got Kat with a really good idea. We got Malia with some, wow, Malia. The formatting for Malia is also fantastic, by the way. But Kat has a really good idea. I really like your idea too, Kat. Can we get a few more? Miles is jumping ahead. Miles is sort of is giving us a different interpretation. But I do like what Miles is saying because Miles is showing us visually what that means as well. We got Kat, we got Malia. Let's get a few more answers in here. Let's get some ideas of when he's moving backwards. So to give you a hint, I'm moving backwards when my position is decreasing. So at what point in time is my position decreasing? Well, here in this section, my position is increasing. That means I'm moving forward. At 50 seconds, I start, I was unaware we're gonna be taking notes. I have a note sheet for us, Kimberly. So try to take notes if you can. Again, this is this will also be on YouTube, so when you watch it, and also the slides are also available. So you can take notes on that. So there's plenty of opportunities for you to take notes. It's okay. It's okay if you weren't able to get all of that. We're walking forwards between 0 and 50 seconds. Here, my position is decreasing. So this, between 50 and 70 seconds, this is when I'm walking backwards. And this is because my displacement is decreasing. Okay, so when am I walking the fastest? Very tricky, very tricky. When am I walking the fastest? Anyone have any ideas? We got Miles with a good idea here. Miles with a good idea. Kimberly with an idea. This one's kind of tricky. This one's kind of tricky. So what I mean by when I'm going the fastest is when is the speed the fastest? When is the speed the fastest? Now I'm going to give you all of you a hint. You know, we have a lot of good ideas so far. I'm going to give you a hint. Now, the slope of a velocity of a displacement resistance line graph is your velocity. The speed of the graph is sort of the absolute value of the velocity. So what we're looking for here is when is the graph the steepest for speed? When is the graph the steepest? When is the slope the biggest? When is the rise over run the biggest? And James here, James has an idea. Adrian has an idea. James, I like how you're thinking, James. Good thinking. Adrian has an idea. It's kind of tricky. And we're looking for when the slope is the steepest. If you're unsure about how to find the slope, you can remember you can just do rise over run, right? How much are you going? So here we're going up 150 seconds. So the slope is 2. Here I'm going from 100 to 40. So I'm going down 60 in 20 seconds. So my slope here is, the slope here is negative 30. But the speed will be 30. We don't care about the negative sign. And then here we're going up 120 in 30 seconds. So the slope here is actually 40. So when am I going the fastest? I'm going the fastest when my slope is the highest. So that is between 70 seconds and 100 seconds. This is when I'm going the fastest. And this is because my slope is the biggest. And the slope here is, I believe, 4 meters per second. Okay, last but not least, when am I standing still? What does it mean by standing still? Standing still means my position is not changing. My displacement is not changing. So when would my displacement be not changing? Mariana with an idea, we got Kat with an idea. So when am I moving the fastest? Well, then when I'm moving the fast, when am I standing still? So when you're standing still, it means my displacement is not changing. So on a graph, on a displacement versus time graph, what this looks like is this looks like a horizontal line. My position is not changing. So where on the graph is it horizontal? It's horizontal between 100 seconds and 120 seconds. Or in other words, my displacement is 1 second. So the time when I'm standing still is between 100 and 120. Does anyone have any questions about this? So let's look for the one up for the fastest. I'm moving the fastest between 70 seconds and 100 seconds. I think Adrian, I think it was the one that you answered. Yeah, you got it, Adrian. You got it. Moving the fastest between 70 and 100 seconds. Yeah. Okay, so the last few minutes, what I'm going to do is I'm going to draw a velocity versus time graph. So this is something that I'm going to show you how to do it. This is because velocity versus time graph is a lot harder to do. Okay. So how to do a velocity versus time graph? A velocity versus time graph is basically how fast are you going at any particular point in time. So there are 3 sections here. We have section from 0 to 50. Wait, 4 seconds. Section from 0 to 50. We have 50 to 70. We have 70 to 100. And then we have 100 to 120. So to figure we want to figure our velocities here. So between 0 to 50 seconds, I go up 100 meters. My velocity is 100 meters over 50 seconds. My velocity is 2 meters per second. So what does this mean? It just means that for the first 50 seconds, my velocity is 2. So what I'm going to do here, I'm going to have my graph labeled. What I'm going to do here is my velocity is always 2 between 0 to 50. I'm going to draw a horizontal line. Actually, I'm going to draw it blue here. I'm going to draw a horizontal line from 0 to 50 at 2, right? It's at 2 because our velocity is 2 meters per second, and our velocity is 2 between 0 and 50 seconds. Okay, so it's also horizontal, very important, because our velocity is not changing here. If it was diagonal, that means our velocity would be changing, and we haven't quite gotten to it. So let's talk about between 50 and 70. Between 50 and 70, my position decreases by -60. So it'd be -60 over 20 seconds. And my velocity would be -3 meters per second. So what I'm doing here is I'm going to at -1, -2, -3. At -3, between 50 and 70, I'm going to draw a horizontal line here. So you can also draw a dead line here. So it's not a smooth transition. It's the velocity will just jump. So you're instantly accelerating, decelerating. So I'll draw a little dotted line here, and then between 50 and 70 seconds, my velocity will be -3. Just for timing's sake, I'm just going to go with the 70 to 100. 70 to 100, I think I talked about it previously. My velocity is actually 4. So between 70 and 100, it's going to be +4. Little dotted line here. And then last but not least, between 100 and 120, my velocity is 0 because I'm not moving. And when your velocity is 0, when you're not moving, you have a horizontal line at 0. Very important, right? It's very important. So we'll do some graphing later on, but I do want you to sort of have an idea of how you can do a velocity versus time graph like this. Okay. So do you need to draw velocity notes? So I would recommend you draw a velocity graph. You don't need to put it in your notes just because I think it'd be pretty hard. I guess you could take a picture and put it in your notes. You don't need to submit a velocity graph when you submit your notes. But I would recommend you draw a velocity graph just like on paper or something, so that way you have an idea of what it looks like. Just because, yeah. So you don't need to submit one, but I would recommend you draw one. So we're out of time here. If you have any questions, you can ask me after class during lunch. So no homework for today. No asynchronous assignment on Wednesday either. What I would do, if you have anything you haven't submitted or if you have anything you need to revise, please do so ASAP. Make sure you submit it before the end of the semester. That is a hard deadline. And if you haven't graded anything in the last few days, but I will be grading throughout the week and I'll be giving you feedback. So, and if you have any questions about your grade or what you should do or what assignments you should do, please reach out to me. Otherwise, thank you all for coming today. I had a great time, good participation, and then you're all free to go, and I will see you all on Friday.
Thank you.
Thank you.
Bye-bye,
Thank you.
bye-bye.
Thank you.
Hope we all had fun today. Bye-bye.